Hello everybody, welcome into another lesson. So I know in the last lesson we talked about converting rectangular equations to polar equations. Well, as it turns out, you can work in reverse, and that's what we're going to do today. We're going to convert polar equations into rectangular equations. And we can use the very same fundamental identities to help us do so. We have r squared is equal to x squared plus y squared, which would have to mean that r equals the square root of x squared plus y squared. Also not forgetting that x equals r cosine of theta, y equals r sine of theta. So with that in mind, let's jump into the first example. So here you have r just equals 6 sine of theta. Well, we know about r. We have the identity for that. The problem is we just have 6 times a sine. It almost looks like r sine of theta, but we're not quite there. We can't do anything with the right-hand side. Well, what if we multiplied both sides by r? If we do that, you'll end up getting r squared equals 6r sine of theta. So now you would get r squared equals 6r sine of theta. Now we have a form we can work with. So what is r squared? That's the same thing as x squared plus y squared. That would equal, on your right hand side, we know r sine of theta is y. That just equals 6y. So to put this in standard form, make the right hand side equal to 0, you'll get x squared plus y squared minus 6y is equal to 0. And that would be the rectangular form of this equation in standard form, which, as it turns out, would give you a circle with the center not at the origin. So let's do another example here, but this time we'll do it with the cosine function. What if we have r equals 2 cosine of theta? So r equals 2 cosine of theta. Again, we know about r. We have an identity for that. Now the right-hand side, we just have 2 times cosine. It almost looks like r cosine of theta, just we don't have the r. Well, if we multiply both sides by r, what you'll end up getting is r squared equals 2r cosine of theta. Now we have a form we can work with. R squared is the same thing as x squared plus y squared, equaling the right hand side. R cosine of theta is x, so that would equal 2x. And the final answer in standard form would be x squared plus y squared minus 2x is equal to 0. That would be the standard form in the rectangular form of this equation. You end up getting another circle with the center not at the origin. Each type of polar equation has its own tricks, just like rectangular equations did to convert to polar. Well, different types of polar equations have different tricks to pull to convert to rectangular. If it's just some coefficient times sine or cosine on the right hand side, you're just going to multiply by an extra r. That's all you're really going to do. But there are other types that we're about to get into. So let's talk about theta is equal to 4 pi over 3. Alright, so notice something. We have no r. We just have theta equals 4 pi over 3. Well, let's just picture the unit circle for a second. If it's saying theta equals 4 pi over 3, that means the whole 4 pi over 3 axis, both positive and negative. So negative of that would be pi over 3. It's really a whole line. You're going to get an entire line. It doesn't specify a radius, but that's okay, we don't need to. How do we approach these types with just theta equal to some angle in radians? It is helpful to remember that x equals r cosine of theta, y equals r sine of theta. What you can do you want to pick two values of r. My recommendations are always 0 and 1. Because what that's going to do is give you 2 points on that line so you can find the slope and therefore find the equation. So let's start with radius equals 0. So if x equals 0 times the cosine of 4 pi over 3, well, 0 times anything is just 0. You'll get an x-coordinate of 0. Then y equals that radius of 0 times the sine of 4 pi over 3. Well, again, 0 times anything is 0. So you have your first coordinate set at the point 0, 0. That's why I say pick 0 as one of them, because you have a free coordinate at the origin. And that makes sense because in the polar axis, this line will go right through the origin, or the pole as it's known in the polar system. Same thing. So that's a free, easy one you can get. Okay, now the next one I'm going to recommend is we pick radius 1. That's probably the next easiest one to go with. What I'm going to suggest is we draw ourselves a 30, 60, 90 right triangle, just to aid us in getting the values. Well, 30 is pi over 6, 60 is pi over 3. Now the side opposite pi over 6 has a length of 1, opposite pi over 3 has a length of the square root of 3, opposite the right angle has a length of 2. So if the radius is 1, x is just going to equal 1 times the cosine of 4 pi over 3, or simply the cosine of 4 pi over 3. Alright, well, keep in mind though, 4 pi over 3 is in the third quadrant, so that's the equivalent of a pi over 3 angle only in the third quadrant. The cosine would be negative. So the cosine of pi over 3 adjacent over hypotenuse is 1/2. If you just negate that, you get negative 1/2. Alright, now we can find y by taking that radius of 1 times the sine of 4 pi over 3. Well, we're in the third quadrant. That means the sine is also negative. So this is going to be a pi over 3 angle in the third quadrant. So the sine of pi over 3 is the square root of 3 over 2. You negate that, you get negative square root of 3 over 2. I should probably make that square root of 3, not 3/2. So negative square root of 3 over 2. So now with radius of 1, you have the ordered pair negative 1/2, negative square root of 3 over 2. You could pick any radius value you want. It's just 0 and 1 are probably the easiest to go with. Now that we've gotten two ordered pairs, let's find the slope. Well, the slope of this line is going to, of course, be your y2, which is negative square root of 3 over 2 minus your y1 of 0 divided by your x2 of negative 1/2 minus your x1 of 0. Well, that's going to just give you negative square root of 3 over 2 divided by negative 1/2, which you have a complex fraction, you'll invert and multiply, and to top it off we have two negatives which are going to cancel out, so you'd end up with positive square root of 3 over 2 times 2 over 1, making your slope just a positive square root of 3. Now that we've got the slope, we can use the point slope form of a line to find the equation. So let's pick 0, 0. That's an easy point to work with. So you'll take y minus 0 equals the square root of 3 times the quantity of x minus 0, or simply y equals the square root of 3 times x. And that would be the equation of the line in rectangular form. This would become y equals the square root of 3 times x. That is the equation of the line, the same thing in the rectangular system. Let's do another angle. I'll leave that triangle up though, because it's going to be based on something similar but a little bit different. Let's say we have one where theta is equal to 5 pi over 6. So I'm going to pick theta equals 5 pi over 6. So this is going to be another line. So let's go ahead, let's just take r being 0. R being 0, so that means x would equal 0 times the cosine of 5 pi over 6. Well, that's just going to give you 0. And then that means y equals 0 times the sine of 5 pi over 6. Well, that's also going to be 0. So you get a free ordered pair at the origin. And then now let's go with r equals 1. That's probably the next easiest one to do. So if we take r equals 1, x would equal 1 times the cosine of 5 pi over 6. So the cosine of 5 pi over 6, well, 5 pi over 6 lies in the second quadrant, which means the cosine is negative. So this will be the same thing as a pi over 6 angle, only in the second quadrant. So what is the cosine of pi over 6? That's square root of 3 over 2. If you negate that, you would end up getting negative square root of 3 over 2. Now what about your y? So that would equal 1 times the sine of 5 pi over 6. Well, 5 pi over 6, again, that's in the second quadrant, but the sign would be positive in the second quadrant. So this is a pi over 6 angle in the second quadrant. The sine of pi over 6 is 1/2, and it's just going to be positive 1/2. So you get an ordered pair, this time of negative square root of 3 over 2, positive 1/2. Now, since we have two ordered pairs, we can find the slope. Let's go ahead and do that. So the slope would be y2 of 1/2 minus y1 of 0 all over x2 of negative square root of 3 over 2 minus x1 of 0. So in short, you just get 1/2 over negative square root of 3 over 2. We have a complex fraction. We have to invert and multiply. So you would get 1/2 times 2 over negative square root of 3. This turns into negative 1 over the square root of 3. And if you rationalize the denominator, you just end up getting negative square root of 3 over 3. So that's your slope, is negative square root of 3 over 3. Now that we have the slope, we can find the line. Let's pick the point 0, 0. So y minus 0 equals that negative square root of 3 over 3 times the quantity of x minus 0, which would just give you y equals negative square root of 3 over 3 times x. And that would be this exact same equation, only in rectangular form, and you get a line. So that's how you would approach angular equations. Now, let's go on to, and these next ones are actually super easy. You're going to see just how easy they are. Let's say we have an equation where r equals 4. So just r equals 4. So you have r equal to a number. Well, as we talked about yesterday, if you have r equal to a number, that's just a circle with a radius. So this is a circle with a radius of 4. how do we convert this into rectangular form? Well, we have r equals the square root of x squared plus y squared. So you would get the square root of x squared plus y squared is equal to 4. Now we just want to get rid of the radical, so we'll just square both sides. You would get x squared plus y squared equals 16. And there's the rectangular form of this circle. It's x squared plus y squared equals 16. Let's do one more of these. And by the way, that's center at the origin. If you just have r equal to a number, the center is always going to be at the origin. So r equals 10, so let's use the fact that r equals the square root of x squared plus y squared. We'll set that equal to 10. Now get rid of the radical, square both sides, you would get x squared plus y squared equals 100. And that would be the equation of a circle with radius 10, center at the origin, in rectangular form. The exact same thing as this. Alright, those were easy. Now let's talk about a couple reciprocal functions. So let's say, for example, we have r equals negative 3 cosecant of theta. So r equals negative 3 cosecant of theta. It's not as bad as it looks. I know this looks really bad, but it's really not. Let's not even convert the r yet. This is going to be the same thing as r equals what? Well, if we have cosecant, isn't that the same as the reciprocal of the sine? So the right-hand side would become negative 3 over the sine of theta, which then means we could multiply both sides by the sine of theta to get the constant by itself. This would turn into r sine of theta is equal to negative 3. Okay, so what's r sine of theta? That's simply y. You just end up with y equals negative 3. So this is the rectangular form of this equation, which just turns out to be a horizontal line through y equals 3. And then we're going to do a similar one, only it's going to be with the secant function. So r equals 2 secant of theta. Alright, so we have r equals 2 secant of theta. Again, this is not nearly as bad as it looks. So leave the r alone a minute. We'll have r equals, now what's secant of theta? Isn't that the same as the reciprocal of the cosine? So that would be equal to 2 over the cosine of theta. Now if you just multiply both sides by the cosine of theta, you'll get the 2 by itself. What you'll end up getting is r cosine of theta equals 2. Well, r cosine of theta is x. So in rectangular form, the equation you should get is x equals 2, which would end up being a vertical line through x equals 2. And the trick is, if you have secant or cosecant, you can just use the fact of the reciprocal trig identities, multiply both sides by what's in the denominator, and get an easy x or y equals a number. So those really aren't that bad. Ultimately, it goes back to these fundamental identities. If you can get it in those forms, understand how they work, you're going to be just fine. Alright. Now let's change it just a little bit. Just a little bit here. Let's say we have something like r squared equals cosine of theta. So we got r squared equals cosine of theta. Well, how in the heck are we going to approach that? Because now the r is quadratic, but the cosine's still linear. Well, for starters, I'm going to suggest we multiply both sides by r. And there's a reason I'm saying that. if we multiply both sides by r, what you'll end up getting is r cubed is equal to r cosine of theta. Now what I'm going to recommend we do, once we have that r, we square both sides. So let's go ahead and do that. So we will take that r cubed, raise that to the second power. That's going to equal r squared cosine squared of theta. The reason I'm doing the squaring is because if you separate r cubed into r squared times r, granted you'll just have x on the right hand side, but what you'll end up having is this whole x squared plus y squared quantity times the square root of x squared plus y squared. And generally speaking, we want to get rid of the radical. So we're not even going to bother with that part. That can save you all that grief of an extra radical that we just need to get rid of anyway, and might just confuse you more. So, okay, we have r cubed squared. Well, that gives us r to the sixth would equal the right-hand side. R cosine of theta is x, so really this is x squared. We have r squared equals x squared. Now, what's this business of r to the sixth? Isn't that also the same thing as r squared raised to the third power? Wouldn't that give you r to the sixth? You could say that equals x squared. Well, what's r squared? That's going to be x squared plus y squared. So actually your final answer in rectangular form would be the quantity of x squared plus y squared raised to the third power would equal x squared. And if you want, you could try to use the binomial theorem and expand this and get the x squared over here, but it's really not going to make a difference. This is probably the simplest way to write something like that. You would just end up with x squared plus y squared quantity to the third equals x squared. That's the best way you can deal with this. Alright, let's do another similar one. It might actually be just a little bit different. So we're going to have r squared equals the sine of 2 theta. So this is a bit different than the last one we did, but it's the same in the regard that you have r squared equal to a trig function. Well, let's just ignore the r squared for a second. Let's focus on sine of 2 theta. This is a double angle identity for the sine function. If we remember our double angle formula for the sine function, the sine of 2 theta, that is the same thing as 2 times the sine of theta times the cosine of theta. That's why trig identities, especially your double angle formulas, are very important, especially knowing the sine of 2 theta and the cosine of 2 theta. Those are very important. Okay, so we got the double angle formula. Let's input that into where sine of 2 theta is. So you'll get r squared equals 2 times the sine of theta cosine of theta. Alright, well, here's the thing. We just have 2 times some trig functions. If we had the r's with each of those, we could actually work with it. If we multiply by an r and put it in between the 2 and the sine, and put another r in between the sine and the cosine, technically we're multiplying both sides by r squared. So let's do that. So we're going to multiply both sides by r squared, but we'll place an r between the 2 and the sine. You'll have 2r sine of theta times r cosine of theta. which means since we multiplied by r squared on the right, we got to do it on the left. You would have r to the 4th power on the left. But the good news is, on the right-hand side, we have a form we can work with. So, on the right-hand side, our sine of theta is y, our cosine of theta is x, so this would really just turn into 2xy. And then, well, okay, r to the 4th, isn't that the same thing as r squared squared? Well, what is r squared? That's actually x squared plus y squared, so you would have the quantity of x squared plus y squared raised to the 2nd power equals 2xy. And that would be probably the best way we could do this for the rectangular equation. So if you have an r squared, you're almost always looking to manipulate the right-hand side by multiplying by some factors of r. And sometimes you have to square both sides again. It's just knowing when to do it and not. Last exercise, we squared both sides after adding the r. This time we didn't have to, because both sides were already squared after we added the r. So the idea is, in general, you just want to get rid of this radical. You just don't want to have it. That's how you would know you want to square or not. Just don't have a radical. All right. Now, I got 4 more left, and these are going to tie into a couple lessons from now when we talk about the polar equation of a conic section. So the next 4 are all conic sections. So what do we got here? These are different than what we've done yet. So we have r equals 1 all over 1 minus the cosine of theta. As this turns out, this is going to be a parabola, which we'll talk about in a few lessons from now. But how might you approach something like this? Well, it's not as bad as it looks. If we remember from the previous lesson, when we had this in rectangular form, it was decently tough to convert it into polar form. Working the opposite way, it's actually not that bad. All you're going to do is multiply both sides by 1 minus cosine of theta, get rid of your denominator. So what you'll end up with is r times the quantity of 1 minus the cosine of theta is equal to 1. Okay, so now you'll have r minus r cosine of theta equals 1. Well, what's r cosine of theta? That's just x. So this would turn into r minus x equals 1. Well, then this would turn into r equals x plus 1. So what's r? That's the square root of x squared plus y squared is equal to 1. Well, in general, we don't like to have a radical, so let's square both sides. Well, it equals x plus 1, excuse me. So you would end up getting x squared plus y squared equals the quantity of x plus 1 squared. Now we just have a simple binomial squared on the right-hand side, so you'll have x squared plus y squared equals x squared plus 2x plus 1. We're almost there. So we ultimately, to get this in standard form, we want to make the right-hand side equal to 0. So subtracting x squared from both sides, that just leaves y squared by itself over here, minus 2x minus 1 equals 0. And that would be the final form, the final answer for this equation in rectangular form. You would get y squared minus 2xy minus 1 equals 0. And there is your parabola. I got 3 more. Well, technically it's 2 conic sections, then 1 line, but the last one we do is going to look like a conic section, but it's not. Alright, so we have r equals 2 over 1 plus the sine of theta. So we have r equals 2 over 1 plus the sine of theta. Well, again, and notice with the last one we did, this one, and you'll notice the same pattern in the next one, what you're going to want to do if you just have one trig function in the denominator is apply what we're doing now. Multiply both sides by what's in the denominator to get rid of your denominator. So this would turn into r times 1 plus sine of theta is equal to 2. So then distribute your r, you'll get r plus r sine of theta is equal to 2. Well, what's r sine of theta? That's just simply y. So you would have r plus y equals 2. So then r equals 2 minus y. Well, we're almost there. What we want to do now, because r truly equals the square root of that x squared plus y squared, you would set that equal to 2 minus y. We want to get rid of the radical, of course. So square both sides, you would end up getting x squared plus y squared equals that quantity of 2 minus y raised to the second power. Then you just have a simple binomial squared, so you would have x squared plus y squared equals 4 minus 4y plus y squared. And now we just want to make the right-hand side equal to 0. The x squared will stay, but the y squared will be gone. Then you would just have plus 4y minus 4. That would equal 0. So the final form of this in rectangular form for this parabola is x squared plus 4y minus 4 equals 0. Alright, one more conic section, then we have another type of line. Alright, so r equals 6 all over 2 minus 3 sine of 3. So notice here, just notice this a minute, we don't have a single one of these equaling 1 for any of our coefficients or constants. Now, as this turns out, in 2 lessons from now, we're going to talk about something called eccentricity of conic sections. Then after that, we'll talk about the polar form of conic sections. But this is going to actually turn out to be a hyperbola. But let's go ahead here. You're going to approach this the same way. Get rid of your denominator by multiplying both sides by the denominator. So this would turn into r times 2 minus 3 sine of theta. That's going to equal 6. So this would turn into 2r minus 3r sine of theta is equal to 6. Well, what's r sine of theta? That's simply y. So this would turn into 2r minus 3y is equal to 6. So then you would end up getting 2r equals 3y plus 6. Alright, now what's r? That's that square root of x squared plus y squared. So this time you'd have 2 times the square root of x squared plus y squared is equal to 3y plus 6. Well, we want to get rid of the radical, so let's go ahead and square both sides. If you square both sides, you would end up getting 4 times the quantity of x squared plus y squared is equal to that 3y plus 6, that quantity raised to the second power. So distribute the 4, you would get 4x squared plus 4y squared is equal to this binomial square, so 3y squared would give you 9y squared Alright, 3y times 6 is 18y times 2. That's actually going to be 36y. Plus that 6 squared, that's just plus 36. And now we just collect like terms, make the right-hand side equal to 0. You'll end up with 4x squared minus 5y squared minus 36y minus 36 equals 0. And that is the equation of this hyperbola in standard form in the rectangular system. You get 4x squared minus 5y squared minus 36y minus 36 equals 0. Now I got just one more, and as it actually turns out, it's just going to be a line, though it's not going to look like it at first. Alright, so we have r equals 6 over 2 cosine of theta minus 3 sine of theta. Okay, well, notice something right away. We have two trig functions in the denominator. So far today, with the lines, first we talked about vertical lines or horizontal lines, where you have either secant or cosecant functions on the right-hand side. You have theta equal to some angle. Those are going to be your classic slanted lines with no constant added to them. Now these, as it turns out, will turn into the general standard form of the equation of a line in rectangular form. So the approach here is the same as what we did with the other ones, and believe it or not, this is actually going to be easier. Multiply both sides by the denominator to get rid of the denominator. You would have r times the quantity of 2 cosine of theta minus 3 sine of theta, all that equal to 6. So distribute your r, you'll get 2r cosine of theta minus 3r sine of theta equals 6. Well, r cosine of theta is x, so you end up getting 2x minus r sine of theta is y, so minus 3y would equal 6. So you could write your answer like this in standard form, or another way it's considered standard form is if you make the right-hand side equal to 0, it would be the same thing as 2x minus 3y minus 6 equals 0. Either of these two answers would be correct for the general standard form of the equation of a line. So if you see two trig functions in the denominator, that means you're going to have some other constant for the equation of your line. Okay, so that's it for this lesson. Next lesson I'm actually pretty excited to teach. That's going to be a fun one that I think a lot of you are going to like. We're going to graph polar equations. And we're going to get some shapes unlike anything you've ever seen before in a math course. If any of you know what spirographs are, or those type of things, or you ever drew flowers or stuff like that, or really pretty curved drawings, well, that's what a lot of polar graphing is. So I hope you're ready for that one. I'm looking forward to teaching it. So I hope everybody has a great day. Take care.